Thank you everybody for coming. So our first speaker today is Dessauges-Zavadsky, and she'll be telling us about star formation in molecular clouds in cosmic known galaxies.
Thank you. So I would like first of all to thank the organizer for inviting me to present you my research on the star formation cycle from molecular clouds to star cluster complexes in galaxies at cosmic noon. So it's really a great pleasure to attend this conference in the beautiful town of Pisa. So as we have already heard during this conference, the spatially resolved deep HST images have revealed that galaxies at cosmic noon have very perturbed morphologies, characterized by bright knots popping up over the diffuse light of galaxies as illustrated in these images. And this was a striking result, all the more that more than 60% of galaxies at redshift between 1 and 3 are showing these clumpy features. So the advent of James Webb definitely confirms the ubiquity of such UV bright clumps in galaxies up to redshift of 10, as we have heard yesterday in Angela Adamo's talk. So since the discovery of these UV bright clumps, the long-standing question remained on their origin. So are these clumps star-forming regions formed in situ in host galaxies? So similar to the nearby star-forming H2 regions with stellar masses of the order of 10 to the 4 to 10 to the 7 solar masses for 20 to 100 parsec skies, which encompass several star clusters with radii smaller than 10 parsec? Or are they accreted satellite remnants following a merger event, as also observed in the universe in some post-merging systems? So irrespectively of the origin of these clumps, their study is important for several different reasons that are listed here. And in this review, I would like to focus on the following 3 items. First, the use of clumps to determine how galaxies assemble their mass. If clumps are star-forming regions formed in situ, they should contribute to the recent star formation and the stellar mass buildup of galaxies. And if, on the other hand, they are merger remnants, they should allow to trace the merger activity of galaxies. Second, clumps are useful to trace possible changes of the physical properties of star-forming regions across cosmic time. And third, clumps can help us to understand the star formation process in high redshift galaxies at small scales and determine if this star formation process varies or not across cosmic time. For this, we need to assess, as we will see, both the parent molecular clouds and the UV bright clumps. So let me start with the clumps and the galaxy mass assembly. So over the last years, several observational findings that I will review have shown that to support actually that most of the UV bright clumps, at least at cosmic noon, are star-forming regions formed in situ in host galaxies. So clumps hence favor the secular galaxy mass assembly, and these observational findings are the following. So first, back to 2016, Shibuya et al. Determined the evolution of the clumpy galaxy fraction from redshift 0 to 8, shown here in blue, and they found that it follows the cosmic star formation rate density evolution shown in black, but does not agree with the evolutionary trends of major and minor merger shown in red and in green. So these results was further confirmed by recent HST analysis of Satari, which even shows a possible trend of increasing clumpy fraction at higher redshift. Second, Shibuya also found that the clumpy galaxies shown here by the red histograms are dominated by disk-like systems with Sersic indices of 1. And third, Elmegrin and collaborators nightly determined that edge-on clumpy galaxies shown in the right panels have comparable disk scale heights to the edge-on spirals without clumps shown in the left panels. And finally, the kinematics of the majority of star-forming galaxies at cosmic noon, including the clumpy galaxies, have been shown to be dominated by order disk rotation and not by perturbed kinematic properties, with the rotation-dominated fraction reaching up to 60% at redshift of 2. Nevertheless, we know that this high redshift disk, as we have heard yesterday in Diane's talk, is that they are very different from local counterparts. They are characterized by much higher velocity dispersions than local galaxies, and they have also higher molecular gas fraction, together resulting in being marginally stable disks. And therefore, based on numerical simulation, it has been proposed by several authors that these high redshift gas-rich and turbulent disks are subject to violent gravitational instability caused by intense gas accretion flows and fragment to form in situ gravitationally bound gas clouds, which are believed to be the birthplaces of the observed UV bright stellar clumps. So in conclusion, several observational findings that I have just reviewed support this in situ clump formation and the secular mass assembly of galaxies, with clumps being most likely formed by fragmentation of gaseous disks. So what are the clump's physical properties? So the main difficulty, as we have also heard yesterday, is to achieve sufficient spatial resolution to be able to probe the intrinsic physical properties of star-forming clumps hosted in high redshift galaxies, knowing that the star-forming regions and even individual star clusters have sizes of the order of a few parsec, and that scales below 500 parsecs at redshift larger than 1 cannot be resolved even with James Webb. So as a result, sub-100 parsec scales at high redshift are only achievable with the help of strong gravitational lensing. So for this reason, the detected clumps were initially believed to be very massive, with a median stellar mass as high as 10 to the 8 to 10 to the 9, and with more than kiloparsec sizes. This initial picture was revised back in 2017 when considering a few at that time strongly lensed galaxies in which the sub-100 parsec resolution allowed us to release the blending effect of clumps, and when also considering very deep observation from HST ultra-deep field surveys with very good sensitivities, which allowed us to weaken the clump mass bias at the low mass end. And the compilation of clumps hosted in both lens galaxies, shown in the green histogram, and in the Hubble ultra-deep field galaxy, shown in the red histogram, revealed a clump stellar mass distribution shifted by 2 orders of magnitude to lower masses, reaching a median of 10 to the 7 solar masses with sizes smaller than 300 parsec. And these revised clump stellar masses were also found to be in nice agreement with stellar mass distribution of clumps predicted by simulation and formed through disk fragmentation, shown by the blue histogram. So the intrinsic stellar masses and sizes of high redshift clumps are now further confirmed with the recent James Webb observation. And Angela Adamo presented yesterday our first analysis of 18 galaxies lensed by SMAX 0723, leading a sample of 200 clumps at redshift larger than 1, and the more recent analysis of clumps in galaxies lensed by Abel 2744, in which Adelaide Claessens did really the heroic work to analyze 484 galaxies at redshift from 0.7 to 10, yielding to a sample of more than 2,000 clumps. So in what follows, I will focus on the redshift range between 0.7 and 5.5, encompassing the cosmic noontime. So this new compilation of clumps confirms in these histograms that the median stellar mass are indeed of the order of 10 to the 7 for any redshift bin from 0.7 to 5.5, with clumps ranging between 10 to the 4 and 10 to the 9, 9.5 for the most massive clumps, which appears to be the central clumps associated with the proto-bulges. The clump radia range between 1 to 600 parsecs, with 75% being smaller than 200 parsecs and 37% being smaller than 100. This shows that we are clearly now entered the era where we are able to probe statistically resolved star-forming regions down to individual star clusters. And the clump ages distribution seems to evolve with redshift, since the median ages decrease from 30 million years for low redshift clumps to 20 million years for high redshift clumps. And we don't find clumps older than 500 million years in the high redshift bins, and in the lower redshift bins, most of these clumps are also younger than 200 million years, which suggests that most of them cannot survive more than these 200 million years. We also find that clams have significantly higher star formation rates toward higher redshifts. And in summary, there seemed to be a trend, as Angela said yesterday, of clams being more massive, younger, and star forming towards higher redshift. So with Matteo Massia, we further analyzed the redshift evolution of the clam star formation rate density via Villanueva distributions, and limiting the sample to the most compact clams with sizes lower than 100 parsec to prevent from being affected by spatial resolution effects. A clear redshift evolution of the star formation rate density is observed up to redshift of 3.5, and this evolution at earlier cosmic times seems to be less significant. So as a result, this shows that clams seems to significantly contribute to the recent star formation of the host galaxies toward higher redshifts. And the star formation rate surface density evolution can be linked, in fact, to the increase of the galactic scale star formation rate with redshift. We further investigated the stellar mass surface density evolution. So we plot here the corresponding violent distribution as a function of redshift. And contrary to the star formation rate surface density, there is no clear trend for the stellar mass surface density evolution, as shown by the dotted violent distributions, except when considering clams with radii smaller than 20 parsec, namely at scales close to the star clusters, shown here by the field violent distribution. So this redshift evolution likely reflects the ambient pressure where star clusters form, with galaxies at higher redshift being characterized by denser ISM environment. So globally, high redshift clams span 5 orders of magnitude in stellar mass surface densities. And as we already heard also yesterday, many clams actually share similar properties to those of nearby massive clusters, shown by the dashed line here, and some even have densities comparable and even higher than those of typical globular clusters, shown here by the solid line. So finally, this expanded compilation of clams' physical properties enables us also to confirm the first constraint we obtained with Angela Adamo back to 2018 on the stellar mass function of clams at redshift between 1 and 3, and which we found at that time to be following a power law with a slope of -2. So this is in line with the hierarchical structure expected to apply if clam formation results from the turbulent-driven fragmentations, as the gravitational fragmentation and turbulence compression are scale-free processes. And such a power law distribution is in fact characteristic of local star clusters and star-forming H2 regions, which are hierarchically organized from parsec to kiloparsec scales. So here I show the cumulative stellar mass distribution of clams for 4 different redshift beams obtained for the 2000 clams length by Abel 2744, and they are found to be consistent with a power law distribution with a slope of -2, and this irrespectively of the clamp redshift. So this suggests really a continuity in the way the largest current star-forming units are formed in galaxies from redshift 0 up to redshift of 545. And what is important is that this log normal function of slope -2, describing the shape of the clamp stellar mass function, provides a strong support to the in situ formation of clamps via turbulent-driven fragmentation. So finally, the key question which remains is, what are the parent molecular gas clouds of these high redshift star-forming clamps, and do we detect them? So I will show that massive and dense gas clouds are detected, whose physical properties are correlated with the ambient ISM conditions prevalent in high redshift galaxies. So since stars form in clusters from molecular gas compression, it is obvious to search for the parent molecular clouds of the UV bright star-forming regions. So again, typical giant molecular clouds in local galaxies have masses between 10 to the 4 to 10 to the 7 solar masses and radii of 5 to 100 parsecs. So again, achieving such spatial scale and gas masses in high redshift galaxies is observationally challenging, and again needs the help of strong gravitational lensing, given that ALMA higher resolution observation performed at redshift larger than 1 were obtained at 0.4 arcsecond resolution corresponding to 200 parsec at this redshift. So the search for these molecular clouds is not new. Over a decade, people have tried to search for molecular clouds mostly in the bright submillimeter galaxies, and this was successful in a few cases. And here we have undertaken the search for molecular clouds in two strongly lensed galaxies, which are main sequence rotation-dominated galaxies at redshift 1. There is the cosmic snake on the left and A521 on the right. So they are characterized by similar stellar masses of a few of 10 to the 10 solar masses and similar star formation rates of 30, and they both have a gas fraction of the order of 20%. So the two galaxies have multiple images. Both have an isolated counter image in the north, which is uniformly lensed and shows the real morphology of the source galaxy. And in the south, we have multiple images forming giant arcs, which provide a zoom in on the internal structure of the galaxies. And there one benefits from very high amplification factors, which allows us to achieve physical scales down to 30 parsec in these redshift 1 galaxies. So the two galaxies have a clumpy morphology in HST Raspberry UV and optical images, in which we detect a dozen of stellar clumps. For both galaxies, we obtained ALMA observation in the CO4 to 3 transition to trace the cold molecular gas, shown here by the yellow and the white contours at a spatial resolution comparable to the HST resolution. So we were able to detect for the first time numerous molecular clouds when digging them in the velocity space of both galaxies. So what are the physical properties of these high redshift GMCs, and how do they compare to local GMCs? So for this comparison, we consider the Larsen scaling relation. So on the left, I plot the first scaling relation that shows the linear dependence of the mass of local GMCs on their radius, shown by the gray data points, in implying a constant molecular gas mass surface densities of about 100 solar masses per parsec square. And on the right, I plot the second scaling relation that shows the dependence of the velocity dispersion on radius and calibrates actually the surface density of virialized clouds. So the GMCs at redshift 1, which are shown here by the magenta and orange crosses, are clearly offset from this Larsen scaling relation. They have larger molecular gas masses by 2 orders of magnitude and higher gas mass surface densities by 1 order of magnitude with respect to local GMCs, reaching thousands of solar masses per parsec square. And they also have larger internal velocity dispersion, which is expected if they have to be in virial equilibrium given their larger densities. So such variations in the physical properties of GMCs hosted in different ISM environment has already been reported in some specific nearby galaxies. And in fact, the properties of high redshift GMCs resemble those of GMCs found in local mergers and starburst galaxies, which are shown here by the black circles. So this confirms that the GMC physical properties are strongly coupled to the local and global host galaxy ISM environments, as evidenced in nearby galaxies. So the measured, in fact, large internal velocity dispersion of these GMCs at redshift 1 reflect their 2 orders of magnitude stronger internal pressure in comparison to local GMCs, as shown here in this figure. And this is, in fact, in line with the fact that we have a 1,000 times stronger hydrostatic pressure in the disk midplane of this high redshift disk compared to the Milky Way disk. And as a result, at the formation, what we see is that the GMCs have to have the density, internal turbulence and pressure adjusted to the ambient ISM conditions to enable them to survive the local environment. So since we have identified GMCs and stellar clumps in the same galaxies and at a comparable spatial resolution, this allowed us also to provide an estimate of the efficiency of star formation at GMC scale from the comparison of the GMC masses with star-forming clump masses shown in the left panels. So what we get is an efficient star formation of about 30% in these redshift 1 GMCs, and this is much higher than values lower than 6% reported in nearby GMCs, as we have heard yesterday. So how can we explain this possibly enhanced star formation efficiency? So what we observe is also that GMCs at redshift 1 are found to be highly supersonic with 10 times higher Mach numbers than local GMCs, and this enhanced supersonic Mach turbulence may imply, in fact, a higher efficiency of star formation, since stars are expected to form by gravitational collapse of shock-compressed density fluctuations which are generated from this supersonic turbulence in molecular clouds. So these high star formation efficiencies are consistent with some numerical simulation which do predict a dependence on the star formation efficiency on the gas mass surface density of molecular clouds. And as a result, this may suggest that the star formation efficiency varies across cosmic time and is likely increasing toward higher redshift. And if this is confirmed, this would be an important result that would fit, in fact, many of the GMC discoveries beyond redshift of 5 that are advocating the need of a higher star formation efficiency to explain, for instance, the ultramassive optically dark galaxies discovered by Xiao et al., the ultramassive quench galaxies detected in the first gigayear of the universe by De Graaf et al., and also the high mass end of the stellar mass function of galaxies larger than 4 to 9, at redshift larger than 4 to 9, derived recently by Weibel and collaborators. So to confirm this possibly enhanced star formation, we now need to obtain the H-alpha emission map at the same spatial resolution to our ALMA-CO observation. That means at 0.1 resolution. And why H-alpha? Because H-alpha, as you know, is our best tracer of the very young massive stars, younger than 5 million years. And H-alpha will thus guide us in the identification of the very young clumps recently formed in our detected molecular clouds. And moreover, if we wish to probe the GMC life cycle, we need to link the GMCs with the very young H-alpha star-forming regions, as we have heard yesterday in the talk by Andrea Romanelli. And in fact, by comparing the location of dense molecular clouds with H-alpha star-forming regions, we will be able to answer the following question: do GMC live for a similar time scale or much longer than massive stars? So in the first case, gas and young stars decorrelate on small scale because of the rapid cycling where the newly born massive stars destroy the GMCs as observed in the local Funks galaxies. And in the second case, gas and young stars will be correlated on small scale such that GMCs are in a quasi-equilibrium and will form stars over many dynamical times. So we wish to determine which scenario applies to the high redshift GMCs, and to answer these questions, we have recently obtained near-spec IFU observation of the cosmic snake galaxy at redshift 1. So on the left, I show here the HST RGB image of the cosmic snake with rest frame UV clamps shown in blue and rest frame optical shown in red, and the ALMA CO contours shown in cyan. So on the right, I show the GWST H-alpha map that we obtain with the stellar clumps and CO gas clouds overplotted. So we see that we detect a lot of H-alpha star-forming region, with some being co-spatial with the UV clamps or rest frame optical clamps, and with also gas, CO gas clouds, and some being undetected in HST continuum and CO emission. So the quality of the near-spec IFU is such that we can detect several emission lines for individual stellar clamps. So we see differences in the line strength for rest frame UV clamps with GMC associated, rest frame optical clamps co-spatial with CO emission, and H-alpha clamps with no HST continuum nor GMC associated. So we are now working out the numbers to obtain an accurate estimate of the GMC star formation efficiency at redshift 1 to characterize the H-alpha clamp properties and get a constraint on the GMC life cycle. So since I'm running out of time, I leave you here with my conclusion. Thank you. Oh.
It was very, very beautiful. I was wondering, especially in the second part, what is the role of the lens models of the clusters? Because how much of the results depends on how good you know the reconstruction of the lens model.
So what is important is two things. You have to know the robustness of your model to have a good accuracy on the magnification factors. So as long as you go for the densities, we don't care about this accuracy because it's a ratio. And then the other thing which matters is also that your accuracy of the position of the source plane accuracy position have to be better than your resolution, observational resolution. So this is why we need really very good modeling, but usually for these cluster lenses, it's much more accurate than galaxy-galaxy lensing. And now we get a lot of spectroscopic redshift, so we have a lot of lensed galaxies, pairs, multiple images that allows us to constrain these models on large scales. And then we can also fine-tune, thanks to the detection of clamps, the multiple images of these clamps themselves within, for instance, an arc. This allows us also to fine-tune the lens modeling accuracy within these smaller regions. Oh my God.
Thanks for the great talk. So massive galaxies at cosmic noon are pretty dusty, and a lot of their star formation is often dust obscured. So I was wondering what fraction of these UV clumps what fraction of the star formation, the total star formation, is being contributed by these UV clumps? And then can you comment on how your star formation efficiency picture might change?
Yeah, so this
dusty
is why,
galaxies
this is another reason why we wanted to go also for H-alpha, which is a bit less affected than the UV clumps for the dust obscuration. We do have also, with the CO maps, of course, the millimeter dust continuum maps. And for instance, in A521, we do not detect any dust emission in this galaxy. So this means that globally, what we also observe, that we will observe from the H-alpha over H-beta line ratio, we will have also local maps of dust attenuation. So this galaxy is very fine with AV obscuration very low. And for the cosmic snake, we do observe dust continuum. So it will be, this I have never published because, anyway, but it's another story. But we do observe, that is very interesting, that we do observe also detect some clamps in the dust continuum map.
Do you have Passion Alpha?
Sorry?
Do you have Passion?
No, unfortunately not at redshift 1, it is out of the shade.
Thanks so much for this amazing review. About the masses of clumps, you showed two things. One, that the old results used to show very high masses of 10 to the 8, and then once you looked at the lens galaxies, they came down. And then when you did a whole thing, you found a very wide spread. Is the clump mass in any way proportional to the galaxy mass or to the disk mass? If you were to look at M clump over M galaxy, would all the results converge to a much narrower distribution?
I didn't have time to show some plots, but we have investigated with these numerous now clamp detection the trend of how the clamp mass distribution varies with the galaxy mass. And actually, we do observe that, if I'm not wrong, maybe you can correct me. I can show you the plots, but there is a trend that this slightly changes. It's not significant, but there is a change. What changes a lot, this is very interesting, is the fraction of the clump mass compared to the host galaxy mass. This is changing as a function of the host galaxy stellar mass. And what we observe that the less massive galaxies actually have a higher mass fraction in the clumps compared to
in the
high
total
mass
clumps or in each individual clump?
if you sum up all the individual masses in clumps, yeah.
Thank you.
Is it surprising that the mass function of clumps does not evolve with redshift, while the interstellar medium conditions do so?
So I passed very quickly because it was a problem of time. Where it is. In fact, we observe a slight trend. I can show you later also that the slope doesn't change, but on average, we do observe that at higher redshift, the clumps are slightly more massive. So we do form, on average, more massive clumps in high redshift galaxies, but always following the same hierarchical slope.
The normalization stays the same.
Yes, yeah. Yeah, you mean at the low mass and the normalization, yeah. So this is still maybe subject to, it was there. That's why we didn't, oh, sorry, it's, okay. I think it is here, yeah. It seems to be, so we have changes also toward the high mass end of clumps depending on the redshift. Yes, thank you.
Okay, yeah, thank you.
All right, our next speaker is Tacchella, who will be talking to us about the regulation of star formation.
Okay, yeah, good morning. First I want to thank Bianca and Benedetta and the organizers for inviting me here and also giving me the not so easy task to review regulation of star formation at cosmic noon and beyond. So we will be zooming out, basically leaving kind of the well-resolved system, zoom out onto cosmic scales, but then also zooming in on some of the earliest galaxies we know today. But as we have heard yesterday, I think as well, is basically that galaxies are shaped by a wide range of different physical processes, ranging on a wide range of different spatial scales. And I want to highlight here that this also translates actually into a wide range of different temporal scales, where we have large-scale processes, regulating the star formation on long time scales, and small-scale processes regulating the star formation on short time scales. And so they are imprinting themselves also into the physical properties and their variations with cosmic time. For example, the star formation history of a galaxy, as we can see here. So when we think about, looking back in time, we can of course look at the cosmic star formation at density in the universe that started out very low at the highest redshifts and then was ramping up during the epoch of ionization, reaching a peak at cosmic noon and has been decreasing since then. And this has been mapped out very well with Hubble and many other telescopes also on the ground. And now with JWST, we are really able to basically understand galaxy formation evolution much better towards earlier cosmic times because we are able to probe the rest frame optical up to about redshift of 8 or 9. So what are the key questions that we can answer now, in particular thinking about the epoch of ionization is really, when and how do actually the first galaxies form and also the black holes in them, how do galaxies chemically enrich? But then when we think about the structure of galaxies, we can of course understand how do actually the bulges and disks in galaxies form and evolve and how is this related to the regulation of star formation. Now, one of the key scaling relations when you think about star formation has been the star forming main sequence, so this relation between the star formation rate of galaxies and their stellar masses, and it has been mapped out basically throughout most of cosmic time already, out to at least redshift of 6, And one key feature there is that you can see that the normalization of the star formation sequence, basically the specific star formation rate at fixed stellar mass, is increasing towards higher redshift. So we can see that today's galaxies have roughly a specific star formation about 10 to the minus 10 per year, but at higher redshifts, basically beyond cosmic noon, we see that galaxies double their mass every few tens up to hundreds of millions of years. And so we would say that when we look at the local universe and say like, oh, there's a galaxy with a very high specific star formation rate, this must be a Euler, this must be a merger. But we have learned over the last 10 or 20 years that these galaxies at high redshifts are actually not sustained through mergers and short bursts, but their star formation is really sustained through long periods of gas accretion, basically. And so there was this picture basically developed through both observations and simulations and even simple analytical toy models of self-regulation, where basically if you have more gas accretion, the gas mass goes up, the star formation rate goes up. This means that the gas gets consumed into stars, and those stars also produce feedback, which then leads to a decrease in the gas mass. And so you have this kind of self-regulation going on. Now, we can of course build with this idea a very simple galaxy formation model. So here what I'm showing you is basically on the CDM you have dark matter building up from the bottom up. If you assume that the star formation rate in a galaxy at a given halo mass and redshift is just some star formation efficiency times the gas accretion, the baryon accretion, you can actually explain a lot of the scaling relations we observe. And in such a model, we can assume, for example, that the star formation efficiency only depends on halo mass, and you can tune this to a stellar mass function or a luminosity function. You can see that the star formation efficiency here has this peak around a halo mass about 10 to the 11 solar masses. And you need more complicated models to then explain, for example, why there is this shape, and you can come back and tell me that, oh, this is because of stellar feedback regulating the growth at low halo masses and maybe black hole feedback at higher halo masses. So if you take such a model, you can actually explain the cosmic star formation at density very naturally. The increase at early times is because you're building up halos. You're basically having a strong increase in number density of halos that are able to host galaxies that form efficiently, and also these halos accrete very rapidly. And then you have the peak and the decline because the accretion rates onto halos drop, and some of the galaxies also stop their star formation, which we call usually the quenching of star formation. Now, such a model can actually also explain the star forming main sequence, its normalization, the slope, and even the high mass bending. So you can just see here a few of those models. And this is, I think, not too surprising, right? Because if you look at dark matter, if you think about dark matter halo growth, there is also what we maybe call a dark matter main sequence, where you have basically the mass accretion onto halos is actually directly proportional to the halo mass itself. So again, if you just basically link halo accretion to star formation, you explain something like a main sequence very naturally. And so actually, if you think about it, actually there's basically no model that doesn't reproduce the star-forming main sequence. It comes out very naturally. And I think this is also what Rob alluded to yesterday, where saying like, well, most of these models assume some conversion of gas to star formation. So if you just fuel the galaxies with enough gas and make this proportional to the dark matter accretion, you're very naturally able to produce a star-forming main sequence. And so you need really to have a very strong break in between the baryons and the dark matter to really not reproduce the star-forming main sequence. Now, okay, so we have on the CDM, we have the main sequence and its evolution, but what really defines actually the evolutionary path of an individual galaxy and what regulates its growth? And here I think the crucial point is actually the scatter around the scaling relation. So basically, are galaxies moving around the star-forming main sequence very rapidly, or are they actually growing on kind of longer time scales? And this is important, again, not just for the physics of star formation that I will be talking mostly about in the next few slides, but also for the interpretation of scaling relations, right? Because if you think about, let's say, Milky Way galaxies today, the question is, are all the Milky Way mass galaxies growing up along the star forming main sequence, and can you use the star forming main sequence to trace the typical star formation history of a Milky Way, or actually these star formation histories were decorrelated? So for example, if galaxies stay above or below the star forming main sequence for the Hubble time, you would basically say that galaxies do not grow up together that are equal in mass. Okay, so one thing you can do is you can look at numerical zoom-in simulations, and I'm showing here an example from the Vila cosmological zoom-in simulation, probing mostly galaxies at redshifts 1 to 6. And what you can see here is basically a cartoon picture of the distance of the star-forming main sequence as a function of time or stellar mass as the galaxy grow. And what we find is that these galaxies are actually growing, moving up and down the star-forming main sequence. And they do so because of gas accretion, but also because of how the gas is actually distributed in the galaxy. So what we find is that usually you have a merger or even a counter-rotating stream that can lower the angular momentum of the gas disk. You fuel a lot of gas into the central core of a galaxy into such a compaction event, and you're forming basically a very high gas density in the core, which leads to a high specific star formation rate in the core and the formation of a bulge. And because you consume the gas into stars, and the stars also have stellar winds and supernova, you basically want to quench the galaxy, so the galaxy is actually moving down the star-forming main sequence. But typically at high redshifts where the gas fractions are high and the replenishment times of the disks are short, you are accreting gas, and this happens mostly in the outskirts, and so you have basically this inversion. You have kind of like a gas ring, and a specific star formation profile is rising to the outskirts. And you can do these cycles actually several times and build up the bulge but also the disk at the same time until you successfully quench the galaxy. Now such a model makes strong prediction about the specific star formation gradients across the star-forming main sequence, but also about the gas fraction here and also the depletion time as a function of the distance from the main sequence. Now, if you look at not just zoom-in simulations where you have a few tens of halos, but you're actually looking at cosmological simulations, there was a very nice paper from the Eagle team where they actually tried to understand how important are short-term versus long-term variations in the star formation along the main sequence. And they made the point that indeed on short time scales you have this self-regulation going on, but on longer time scales, halo formation times and the environment are much more important. And this is indeed what we find when we look at, for example, the cross-correlation between the star formation histories of galaxies and the dark matter accretion histories. You can see that there's little coherence on short time scales, so there is again baryonic physics going on, but when you go to longer time scales, you can see that there is more coherence and the star formation rate traces the dark matter accretion rates. And of course you can say, okay, these are numerical models, can we also analytically understand this, and something we have been trying to develop to actually come from the cosmic scales down to the galaxy scales and the clumps and the GMCs. And so we have extended the regulator model to basically say that, well, we expect that the star formation is sustained through GMCs or clumps, and there are basically then two sources of variability in such a model. You can imagine that you are able to feed the galaxy stochastically with gas, which leads to variation in star formation, but you can also see the GMC sampling in certain galaxy regimes. And so when you look at the amount of variation in the star formation history, this is showing you the power spectrum density as a function of frequency or time scale, you can see that on long time scales you're again dominated by the variations in the inflow physics, but on short time scales it's really the star formation process and the sampling of the GMCs you can see. And with such a model you can then go and actually try to understand the stochasticity of star formation in a wide range of different regimes. And so for example in dwarf galaxies, in the local universe, Milky Way-like galaxies, cosmic noon galaxies and high redshift galaxies. And such a model can then directly be tested, for example, through the scatter of the star-forming main sequence, because you can use basically different tracers to observe different variations in the star formation, right? If you put glasses on H-alpha, you're able to see short-term variations. When you put on things like UV or infrared, you're tracing the longer time scales. And so you can use basically the decrease in the scatter on longer time scales to measure how much variation there is in the star formation histories of galaxies. Now there are of course a lot of caveats to this, because you need to really do a dust correction, metallicity effects and MF can all increase the scatter, and that's why there is a challenge there. And so you might say, well, okay, well, I want to just highlight here that this has of course been done also in the local universe out to about redshift 1, where people really rely on comparing emission line and star formation rates, for example, from H-alpha to star formation rates from the continuum to trace the amount of variability or burstiness you have as a function of stellar mass, and most of these results indicate that the variability increases towards lower masses. Now again, there's a lot of challenges with that, and you can say, well, I need to correct for, self-consistently for example, the dust attenuation, the relative dust attenuation between nebular and continuum emission. And so you can go to SED modeling, and we have, I think, made a lot of progress over the last 10 to 20 years about having flexible star formation histories in model the diversity of galaxies and their star formation histories. But there are still, and there are just fundamental limitations to that. For example, that the spectral sensitivity just falls off like as the log of the look-back time, right? So you can learn about variations in star formation on short time scales from the recent star formation history, but you can never learn about the short-term variations, that happened 10 giga-years ago. And so the star formation fluctuations typically have much lower signal to noise than the overall star formation history. And there are still some challenges in modeling self-consistently the emission lines with the broadband photometry, I think. And then of course there's a fundamental limitation that when we look at star formation history, what you're tracing is the combined light of a galaxy that might have assembled from many smaller galaxies that came together, and there is basically a mixing between in situ and in ex situ that is fundamentally a problem to disentangle. So, but there are successes, right? So for example, the gradients across the star-forming sequence is something that we have measured quite extensively. So this shows you, for example, the gas fraction or the depletion time as a function of the distance of the main sequence. And this all shows that basically indeed the depletion times are shorter above the star-forming main sequence and the gas fractions are typically higher. And again, this is consistent with this picture of self-regulation. You can also go to spatially resolved scales, and this is a bit more challenging, again, because you have to correct for dust gradients in the galaxies. And so this is for a very small sample of where we have symphony and HSD imaging quite in detail. So this shows again the model prediction where we go above the star formation sequence have mostly the star formation in the core. So this shows you the specific star formation gradient, whereas galaxies below the star formation sequence are mostly having the star formation in the outskirts. So this is the data, right? So it's kind of all over the place, but indeed you can see that at least towards the lower end of the envelope of the main sequence, you indeed have mostly galaxies forming stars in their outskirts, whereas there is a bit more happening in the central core above the main sequence. And this has been now being done across redshift. So for example, here it shows you results from Manga by Sarah Ellison, where when you go to galaxies above the star forming main sequence, you can really see that there is much more star formation taking place in the central region than in the outskirts, and the opposite case if you go below the main sequence. So now moving beyond cosmic noon towards high redshift. Of course, with JWST there is a lot of results that I could review, and it's a bit too much, I think. So I started mostly talking about star formation activity, and then I'm pushing the redshift frontier. So, but I'm happy to talk about all the other aspects, of course, as well. So can we find bursty star formation at high redshifts? And I think the answer is actually yes. So you can look at, for example, equivalent width distributions now, right, up to redshift 6 very efficiently with JWST, and you can see that the H alpha equivalent width really implies very high specific star formation rates. And when we look at individual galaxies where we model photometry but also the emission lines, you can clearly see there are many objects like these where the star formation rate is really increasing very strongly in the most recent times. When you do this more statistically over a larger set of galaxies, you can look at the star formation rate ratio over 10 million years, over 100 million years, and indeed you can see that there are many galaxies that have a ratio that shows an increase in the star formation history. And so this means that when you look at the strong emission lines, they're of course confusing sometimes us with a Balmer break as well. So there is a degeneracy, you just have photometry based on emission line measures and the Balmer breaks. So you really need emission line measurements to disentangle that, or at least medium band photometry. And then again, what you can also see here is that actually when you look at the errors on the ages, they are actually quite large. And this is just because, again, outshining is very, very important at these redshifts, right? So what you basically see is that most of the emission is dominated by the young stars, and it's really basically impossible to find the older stars in a galaxy. And so you really have to be very careful with not over-interpreting the star formation histories and the ages, because you just don't see the older stars. And so you're really kind of converging onto the prior of your SED modeling. So this is an important caveat to keep in mind. Okay, so these are the bursty systems. The question is, do you also find galaxies that are not in a burst? And the answer is actually yes. They're much harder to find and actually spectroscopically to follow up. So this shows you a nice result from Tobias Loser, a PhD student in Cambridge, where we find this galaxy here. It is actually very blue, but when you look at the spectrum, you don't see emission lines, but you actually see even a Balmer TN4000 break. And so based on this, you can actually already kind of start estimating the star formation history, but you can also do this with different SED modeling codes. And what you find is that there has been indeed a burst of star formation about 50 to 100 million years ago, but now there's basically no star formation at all. And so you expect these kind of galaxies to appear because you have a burst, but then you should also have a downturn, and these are these systems basically. I might wonder, are there also the galaxies that start their star formation? Can we see galaxies that have a Balmer break but also have emission lines? And the answer is actually yes, but they are very rare, right? Because the young stars are actually very quickly erasing any kind of TN4000 break. And you can see this basically here. You can see clearly a break, but also you can start seeing the emission lines. If you look at the emission line ratios, they imply a relatively low ionization parameter, but a high gas phase metallicity. And again, these kind of galaxies are consistent with having had a lot of star formation going on, a decrease, and a very recent upturn again. So in the modeling side, I think such systems are very naturally expected. These galaxies at high redshifts are of the order of 10 to the 7, 10 to the 8, maybe up to 10 to the 9 solar masses. So we're really probing not the quenching of massive galaxies, but actually, and rejuvenation, but really low mass variations in star formation. And you can see this in a wide range of models where we have looked at with a PhD student, Tibor Dom, where we look at models such as TNG, but also zoom-ins again, and you can see that there are these excursions well below the star-forming main sequence for short amounts of time, right? So these phases, these mini-quenching phases are only taking place over a time scale of about 10 to maybe 30, 40 million years. And you might ask, well, why is that the case? And actually, the main causes are kind of wide-ranging. It's mostly related to stellar feedback, radiation, different winds, but also supernova, and the lack of gas accretion that can be related to galaxy-galaxy interaction as well. So basically, where you just have less accretion and maybe a previous burst that lead to the push-out of gas. So this is about the variability of star formation, and of course we can push to trying to understand star formation at even earlier times. And again, we have to keep in mind that at these times, again, JWST is great with the sensitivity, but it probes mostly the UV. You need MIRI to probe the H-alpha, and you can do this for a very few systems, but generally speaking, again, you are kind of in the UV regime. I think a consistent result that has came out from a wide range of different studies is that there is indeed a remarkable constant bright end of the UV luminosity function, which means you have actually many UV bright galaxies already in place quite early on. And so this orange line here, so this shows you the star formation rate density, or the UV luminosity density as a function of redshift. You can see here with this orange line, this is this constant star formation efficiency model that I showed you at the very beginning, so this very simple model. You expect to have this very strong decrease, again, because the number densities of halos that host star formation efficiently is just plummeting basically. But you can see that the observational data now is coming in that is much higher than that. I think there are still a few challenges remaining to really understand this physically. So first of all, even the same data leads to different candidate lists. Candidates here because we are just relied on photometric redshifts mostly. So this is important, so we need to have a spectroscopic follow-up. Then the question is, again, such models typically assume that this is just stellar emission, but of course we could also have contribution from black holes to the UV emission. And then of course we need to be very careful with thinking about how to compare two models. So let me talk a bit more about, let's think about, we have confirmed the distance to these systems, and we say that, well, HN might not be that important, but what are other processes that can lead to this excess of bright galaxies above redshift 10? Well, one thing is actually to increase the star formation efficiency in halos, right? I said before we have this constant star formation efficiency model that might be too simplistic, and there have been several different ideas. I just highlight here two of them. One is the feedback-free starburst from Avishai Deckel's group, where basically you have that the free fall time of these systems at early times is so short, shorter than 1 million years, that you have in this low metallicity regime massive stars that are not yet able to develop winds and supernova, which this means then you're basically having a very efficient star formation. You can also go with, Alvarenzini put forward the idea, in particular thinking about global cluster formation as well, about this overcooling absence of feedback, where you have basically very massive stars that don't go supernova, but actually directly move into basically being a black hole. And so again, there you can have basically, star formation without any kind of regulation. We can also think about increasing generally the scatter between the dark matter halos and the UV, and you can, for example, think about dust variations, metallicity variations, or even IMF variations. Here, again, dust is difficult just because there is overall much less dust at higher redshifts. We can see this when we look at the UV continuum slopes. You can think about more star formation variability, and indeed that might be one of the ideas, that you go more into a cluster regime, forming mostly just individual GMCs or massive clusters you're seeing on. So that might be one of the scenarios that is kind of able to explain the UV brightness. You can also think about generally having a more heavy top-heavy IMF or even POP3 stars. That's something that is more difficult to confirm, I think, but it's something that people are looking into as well. And then, of course, you can think about changing the dark matter model, right? Because everything that I showed you before is based on lambda CDM. But again, there I think the challenge is if you change the power spectrum of the initial density fluctuation fields, the challenge there is just that there is this degeneracy with, you're able to change the baryonic physics as well. And before we change cosmology, I think we should think very hard about the baryonic component. So thinking about actually galaxies that have been spectroscopically confirmed, right? So we are now actually having many galaxies, many candidates above redshift 10, but we are starting also to spectroscopically confirm them. And this is just basically giving you an overview of some of this. So the colored points are basically spectroscopically confirmed objects from different surveys, but the blue crosses are some of the photometric candidates. So I want to highlight those 4 galaxies that were actually the first redshift above 10 or 11 galaxies that were spectroscopically confirmed with JWST. So here are basically the press release spectra, which are a bit dodgy, but what I want to highlight here is basically the compactness of these systems, right? So these two systems have been high redshift galaxy candidates from Hubble, and those have been newly discovered with NIRCam and then spectroscopically been followed up. And so here you can see the spectra, and they don't show strong emission lines at all. What you're seeing and the spectroscopic redshift is mostly inferred through that Lyman break, actually. But thanks to this distance, then, we're able then to go and measure the properties of these galaxies. And what we find is that these systems are of the order of about 10 to the 8, 10 to the 9 solar masses. They have star formation rates of about 1 to 2 solar masses per year, so similar to the Milky Way galaxy. And you might say, well, that doesn't sound so exciting. But actually, when you look at the specific star formation rate, again, it implies that you have a mass doubling timescale of a few tens of millions of years, right? So these galaxies are growing very rapidly. And their compact sizes of a few, tens up to maybe 200 parsecs imply very high star formation rate surface densities of 10 to about 200 solar masses per kiloparsec squared. Now, these systems are not breaking lambda CDM at all. They are actually quite consistent with what you would expect from a few or a single NIRCam pointing. Now, GNZ11, how many minutes do I have left? 2? Yes, okay, good. So GNZ11, of course, is an outlier here, similar to actually this object that has been discovered in the first few weeks from the GLASS team as well. Is actually very, very bright. And because of this brightness, you can, of course, get a much higher signal-to-noise spectrum with the same integration time. And you can see here this wonderful spectrum with a wide range of emission lines. And what we find when we look at the imaging, we can see that this galaxy is probably not alone. There are actually many photometric candidates around this galaxy. So we find about 9 galaxies in a sphere of about 5 co-moving megaparsec. And this would imply that you are looking at a rather massive dark matter halo. Now, I don't have too much time to go into the details, but you can model this with normal SEDs, and you would find that that an extended component in the galaxy is well described with kind of a slightly older component of a few tens of millions of years, and then you can have a nuclear starburst. But when you look at the spectrum, we can find a clear indication that this galaxy hosts actually a black hole, an accreting black hole of the order of about 10 to the 6 solar masses. And so this nicely connects basically kind of different black hole seed formation scenarios with the quasars that we are observing at redshift 6 and 8. And more generally, there have been actually a wide range of different results coming in that show that the black hole masses of these early galaxies are above the local black hole stellar mass relation. So we seem to have very massive black holes already in place very early on. This are mostly inferred through the broadened emission lines, in particular H alpha, but the absence of broad lines in the oxygen 3 line. And so this is, of course, interesting, and this is something that we actually also find when we look at the morphology of galaxies. This is just one example galaxy at redshift 8, for which we can measure the stellar mass and star formation distribution on space-resolved scales. And what I show you here is just a stellar mass surface density profile of this system at redshift 7.4 and compare it to local elliptical galaxies. And the key point here is that, again, you have these very compact cores already formed very early on, although you're still missing a factor of 100 to 1,000 in solar masses. And so the last slide is basically that we keep working on pushing this redshift frontier, and at the end of this week you will hopefully hear from this newly discovered galaxy that is now spectroscopically confirmed at redshift above 14 that has an extended size of 250 parsec and is also extremely bright. So there is actually a lot of interesting stuff still coming in at the highest redshift. So thank you very much for listening.
Hi, thanks for the great talk. My question is about mini quenching. Do we have any sort of maybe theoretical predictions on the timescales for feedback plus like gas recycling that might tell us if that's on the scale of this mini quenching phase?
Yes, so we look at different models, and the timescales actually vary, but they're typically on the order of 10 to 20 to 30 million years. But it's really stochastic. It really matters really what just happened to the galaxy. Was there a small or minor merger? How is the gas coming into the galaxy? And then, of course, the feedback itself is important as well. But the feedback, let's say that's basically galaxy may be invariant because it's related to the stars and the formation of the stars. But the environment, the small-scale environment of what exactly happened to the gas usually, drives the timescale much more. So it's a bit more difficult to then directly link this to, for example, the feedback process itself.
Thanks for that great talk, Sandro. So you talked about how galaxies below the star-forming main sequence tend to be lower star formation rates in their cores and higher in the outskirts, and then vice versa above. down to what redshift does that still hold? Do you see that even when you're down to z less than 1, or is that mostly phenomenal when the gas fractions are really high at z of 2?
No, I mean, I think this result here on the right, here, this is from Mangan. And so this is also shown, basically seen at lower redshift. And I think, again, when galaxies start self-regulating, you might see this, more. I think at the higher redshift, where things are more bursty, there might be less of this, or at least it might be more difficult to trace. Yeah.
Thank you.
You mentioned that the redshift greater than 11 sources do not have emission lines. Can you explain why? Is it dust or why?
Yes. So again, they are typically very faint. It's not that all of them. So like GNC11, which is just at the border, but then there's also the glass object that have emission lines. So when you are going to the brighter galaxies, you usually have the emission lines. So it's really the fainter ones that seem to have an absence of that. And this is partially because of signal to noise. But then there is indeed the question whether this is just because these galaxies have very high escape fractions, so all the ionizing photons basically kind of escape the galaxy and you don't see them interacting with the gas. Or, and that's also a plausible scenario, it's just that you are in a very low metallicity regime. And so when you look at the UV, you don't see C3 or C4 and so on, so you don't see those emission lines. And then Lyman alpha anyways is more difficult to trace. That said, we have also now a detected object at redshift 13 with a Lyman alpha emission line, so that's also possible. So again, it's difficult yet because we only have a few objects to really come up with a coherent story, but it might be a relation between the escape fractions and the gas phase and the metallicities in general. Yeah.
Thanks a lot, Sandro. You said that it's impossible, so the outshining problem and see at all the stellar population.
Mm-hmm.
Is there a way for this Barsi galaxy we're seeing at that we can look with MIRI at them, or are they too faint? Because then we get to the optical, right? Here you are showing only spectra of the near spec essentially, or very blue.
Yes, no, I mean, the longer wavelength you go, that helps. But I mean, one thing is actually to also study the chemical abundance patterns, for example. Mm-hmm. So this is also a good indication for actually how much star formation took place in the past and over which time scale. You can look at, for example, at the massive quiescent systems. There are places redshift 3 and look at the alpha 2 iron, for example. Mm-hmm. But I think there...
they are also massive.
Sorry, yes. But I think a key thing is just to think very carefully about the priors you're using, right? So a lot of, we talk about like flexible star formation histories, but and non-parametric star formation histories, but they usually have a prior that is constant. And if you would ask, well, what would you expect, is actually an increasing star formation history at these early times. So for example, just changing that, can help with not getting into, let's say, an overly massive galaxy regime when we get stellar masses. The other thing I think is what also I think is very important is, for example, when we even look at these optically dark or very red systems, is actually thinking very carefully about how we model the dust attenuation. So one thing that we find is, so for example, it can make a large difference whether you have a flexible attenuation law, so basically allowing for a change from the Calzadi law, or if you just fix the Calzadi law, which means like you know what the attenuation law is, and that's why everything in the UV gives you an age constraint. And so there is, I think, there is also an important
there is a lot to play with.
Yeah.
Thanks.
Should be 15. No? Okay.
Hello everyone. So I am a postdoc at the Observatory of Rome, working with these collaborators. And today I wanted to present one of my recent projects about the evolution of the star formation rate surface density across cosmic time with GWST observations. So when we talk about the galaxy evolution, we usually refer to the stellar mass and the star formation rate of the galaxies, or a combination of the two, which is the specific star formation rate. But there is also another different normalization of the star formation rate by the total area over which it takes place. And this is called the star formation rate surface density, and given by this equation here. And the recent works have proposed that sigma SFR might represent a more fundamental measure of star formation rate, because it is more intimately related to the physics through which galaxies form stars. And indeed, it is related to the fuel of star formation, sigma gas, through the Kennedy-Schmidt relation. But nice correlations are also found as a function of the ionization conditions, or outflow velocity and mass loading factor, as shown by this work of last year by Yerena et al. 2023, which is based on galaxies observed with bundles and atmosphere at redshift 3. So given the importance of this quantity, researchers have started to investigate how it evolves with redshift and how it compares with other galaxy properties. So in 2015, Shibuya et al. Found a strong evolution of sigma SFR between redshift 0 and 4, or about 2x, with HST observations. On the other hand, no or little evolution was shown as a function of stellar mass in all the redshift ranges explored, as you can see here. And this analysis was repeated with much better statistics recently by Salim et al. 2023, who found a very weak dependence on stellar mass with a slope that is slightly increasing for redshift 0 to redshift 2. And this is due to, their interpretation is that there is a contribution of the build-up of galactic bulges at cosmic noon. And now the new frontier has become to use GWST observations to better constrain the redshift evolution of sigma SFR in the higher redshift range, so above 4, where the uncertainty is higher, and also to probe lower stellar masses down to 10 to the 8, 10 to the 7 solar mass. This has been exactly the main goal of my project. And another additional point that I wanted to test in this project is the effect of stellar-driven winds, and in particular of the so-called dust clearing outflows that have been hypothesized by some recent models to explain the overabundance of massive and bright galaxies at redshift higher than 10 that Sandro has shown before in the review talk. So I will come back to this later. So for this project, I selected a spectroscopic sample from the SEARS and GLASS surveys. And the reason is that in addition to sigma SFR, I also want to study other physical properties of the galaxies that can be derived only from emission lines. And the main condition was to have a spectroscopic redshift higher than 4, because this is where these surveys have more statistics, and also because we want to trace the evolution of galaxy properties from intermediate to, let's say, the reionization epoch. And so with this condition, I selected a sample of 230 star-forming galaxies. You can see here the magnitude and the stellar mass distribution. So here you can see, for example, that the stellar masses, they range between 10 to the 7 and 10 to the 10 solar masses. They are derived from Seagull. And then using H-alpha or H-beta-based star formation rates corrected for dust, and also fitting the luminosity profile in UV-Res frame bands with a Sersic function to derive the effective radius, we finally derive a sigma SFR value with this equation for all the galaxies in the sample. This is an example of a Sersic fit for a galaxy in SEARS. And this is the main result of the analysis. We first investigated the redshift evolution of sigma SFR between 4 and 10. Here the red circles are the individual galaxies. And in many cases there are only upper or lower limits on sigma SFR, but they are properly considered when doing the best fit relation, which is shown with this blue continuous line here. And this best fit relation tells you that there is a shallow evolution of sigma SFR above redshift 4 with a slope of 0.16 that is significantly different from 0. When comparing this slope with the predictions of semi-analytic models, in particular I did it with the Sears mock catalog, which is based on the Santa Cruz models, and I also compared with the Ferrara models 2023. These are respectively the cyan dashed line and the orange dashed line. And we found overall a good agreement both in the slope and normalization of this relation. So we also confirm the very weak dependence on stellar mass that is also observed at lower redshift in all the redshift beams that we are sampling. So in redshift below 6 in the left panel and above 6 in the right panel. And, but here the best fit slope is still consistent with 0 within 2 sigma. You may also notice the large difference in the median sigma SFR between the local universe, which is this cyan dashed line below, and our best fit relation at redshift 5. This is about 2.5 to dex of different, and it mainly comes because when we go to higher redshift galaxies, they form on average stars with higher star formation rate, and they are also more compact at fixed stellar mass. So this is both driving this strong evolution from redshift 0 to 5 of this quantity. Then we also found a very nice correlation between sigma SFR and the ionizing condition as traced by the oxygen 3 over oxygen 2 line ratio. This is called the O32 index. You can see the best fit relation, observed one with a blue continuous line. And regarding this relation, in the local universe, a paper by Fleury et al. 2022 have shown that galaxies with sigma SFR higher than 1 and O32 higher than 0.7 in logarithmic scale, they are strong Laman continuum leakers. And in our Sears sample, we found that a significant number of galaxies, approximately 20%, they satisfy these conditions. And therefore, they can be selected as strong Laman continuum leaker candidates. And these are shown as orange diamonds in the top right corner of the plot. And we also went a step further, and we derived an estimate of the escape fraction. This is an indirect estimate with this formula presented by Magie et al. 2023 based on the GLASS survey. And we actually do find also a correlation between the escape fraction and the sigma SFR. Our best fit relation is this black dashed line. And remarkably, this slope is consistent with what has been observed at lower redshift for Laman continuum leakers by the same study of Fleury 2022. This is the blue dashed line. And is also consistent with the slope predicted by semi-analytic models, the cyan and green dashed lines which lie just slightly above our best fit relation. This comes from Naidu et al. 2020. So overall, what we learned from this is that sigma SFR might play an important role for the escape of ionizing radiation in high redshift galaxies. Finally, we come back, we close the loop, coming back to the original question of testing this dust clearing outflow scenario that has been predicted by some models. So ideally, what we would like to do is to test whether galaxies with higher sigma SFR, they have stronger outflows, which means higher outflow velocities or higher mass loading factors. And if the dust clearing hypothesis is true, this should lead to a galaxy that has essentially negligible dust attenuation, so with a very blue ACD. And this should also lead to higher escape fraction, because these outflows are able to create free channels through which Raman continuum photons can leak. So in practice, we cannot test this first step of the scenario essentially because Circe galaxies, which represent the majority of our sample, they are observed at median resolution, so resolving power of 1000, which is not enough to detect and characterize the outflows. For example, with JACE, there is a slightly better statistics of galaxies observed at high resolution, and I think that Stefano is going to talk more about this tomorrow. But in this project, what we did is to test directly whether galaxies with higher sigma SFR, they correspond to galaxies that have lower or higher dust attenuation. So here in parentheses, I also put the specific star formation rate because we need to keep in mind that the original model by Andrea Ferrara, he only considers the specific star formation rate. Even though, of course, these high redshift galaxies, they form stars in a very compact way. We have effective radii of 100, 200 parsec or even less. So by definition, also the sigma SFR must be very high. In any case, I will test this scenario using both quantities, as we will see in a while. So in the first step, we checked for correlations between the attenuation, AV, which I remember is derived from the Balmer decrement up to redshift 7, and above that you don't have the H alpha line, so we use the result from the SED fitting. And on the x-axis there is the sigma SFR, and you can see that there is a slightly positive correlation between the two. This considers the entire redshift range of our work, but even considering redshift higher than 7 here, you can see that galaxies with higher sigma SFR, they cover a range of different attenuation values from 0 up to 2 magnitudes. And so they are not all 0, let's say. We repeated the same exercise for the specific star formation rate. This is the redshift evolution of this quantity that slightly increases with redshift. And we have a significant number of galaxies here that are above the limit set by the models of Ferrara, above minus 7.6, above which we should have this super Eddington star forming regime in which you can launch these radiatively driven dust clearing outflows. And even here you can see that galaxies above this limit, they don't have all 0 attenuation, but they cover a wide range of values between 0 and 1. So AB is the color coding here. So what we conclude from here is that, at least from this analysis, with this approach, there is no indirect evidence for dust clearing outflows at redshift lower than 10. Of course, in the future, what we should do is to improve the statistics of high redshift galaxies, even though this is going to be very challenging because you need very high resolution spectra, the maximum allowed by NIRSPEC, and you also need to probe fainter UV galaxies to probe a more complete galaxy population. But in any case, this is definitely a direction that we should undertake in the future. And so this is the summary and the main conclusions of this work. We have shown the evolution of sigma SFR from redshift 4 to 10, which is shallower compared to the lower redshift range. We confirmed the very weak dependence on stellar mass, also at high redshift, and also the fact that sigma SFR plays an important role for the escape of ionizing radiation in redshift galaxies. And finally, we have also discussed the presence of these dust-clearing winds in high redshift galaxies. So I finish here and thank you for the attention.
Thanks for that talk. So about the stellar mass dependence of sigma SFR, isn't that just a consequence of combination between the size-mass relation and the star-forming main sequence? So yeah, about that second point, the very weak dependence of stellar mass.
Yeah, let me go back to this. So yes, of course, these quantities are all related among each other, but so I would say that this is even a more fundamental quantity. This just tells you that sigma SFR is not very dependent on stellar mass, and as you say, yes, it can be seen also as a combination of these two other relations, but I cannot tell which is more fundamental than the other. So the truth is that all these quantities, they are all related among each other, let's say, and also actually there is in the local universe a slight trend which is not captured by those fundamental relations that you were mentioning, meaning that you might have also a deviation from a flat relation just because, for example, contribution from a stellar bulge that is building up, which we are not clearly seeing in this data. Yes, of course, these quantities are all related, but there is also a secondary dependence which might depend on other physical properties of the galaxies.
Thanks a lot for your talk. I was wondering about selection of the sample and completeness. Could it be that the relation is driven because you are not seeing the one with low star formation rate densities?
Okay, you mean the redshift evolution?
Yes. This one. And all, yeah.
Yeah, so actually, yeah, there is a slight incompleteness when we go to redshift above 8. Here there is, let's say, a different stellar mass limit between redshift 5 and redshift 8, let's say. But in any case, even if we exclude the galaxies at redshift higher than 7.5, where there is this let's say, this strong decrease of the limiting mass that we are able to probe, even excluding those galaxies, we found a similar relation. So because this is a Bayesian fit that considers all the individual galaxies, and since the very high redshift galaxies, they are not so many, they do not affect very much the global fit. But so it is true that we might be slightly incomplete in the high redshift range, but so the same shallow increase is found also if we consider galaxies where the completeness is higher, below redshift 8, I would say.
Thank you.
right, thank you. So my name is Natalia Villanueva. I'm a master's student at the Calvi Institute for Cosmology in Cambridge. And I'm excited to share with you all today some work I've been doing with the collaborators listed here, looking at the size growth of star formation in early galaxies. So we've already heard some quite nice introductions about this idea of trying to understand how star formation is structurally building up in galaxies by being able to trace it with different timescales of star formation. But a lot of what we've heard so far at this conference, I think, has been in the context of clusters or smaller units of star-forming regions. But what we'll be talking about now is kind of on a more global scale of galaxies overall. So, for example, these clumps here that you see in these different star formation tracers, the sizes that I'll be presenting to you kind of are able to average out over these clumpier structures, and we're able to look at these sizes for the galaxies overall. So at high redshifts, like we've heard as well a little bit, the study of morphologies of these galaxies is in its earlier phases. So I show here two examples of the so-called size-mass relation, one of these being rest UV sizes and the other rest optical sizes, so probing some of those different tracers of star formation. But the power of statistical samples is being able to put them on relations like these and then connect them to other scaling relations and other properties of the galaxies to be able to pick at this question about what those physical mechanisms are actually shaping the morphologies of this star formation. So that leads me to the motivation for the specific sample selection that we did in our work, trying to fill in some of the gaps that still exist in these high redshift morphological studies. So we just talked about the large samples of galaxy sizes and being able to use those in different scaling relations and such. But then for the actual morphological measurements in these early galaxies, both because of observational limitations but also limitations in the tools used to measure these sizes, a lot of studies have not yet been able to probe the really compact and lower mass systems. So I'll show in a few slides when we talk about the results how our work and our analysis has been able to actually probe these regimes. And then finally, the idea of those multi-wavelength morphologies to be able to trace the star formation across different timescales and form together this picture of how the size evolution of star formation is changing. And so we look specifically at redshift 4 to 5 galaxies here. It's an interesting redshift range that I think kind of falls in between what a lot of people have studied for cosmic noon and then also kind of epoch of reionization. So it's interesting to look at this kind of in-between time. So then selecting our sample, I was working with JADES, JWST, NIRCam data. So I'll introduce quickly what JADES is. It's a Cycle 1 program together with NIRCam and NIRSpec. And the NIRCam data is focused on really deep imaging, covers goods south and goods north in 8 to 10 bands. So really, if there's any data set, I feel like that would be able to kind of get us those compact sizes, the low mass systems, and also that multi-wavelength approach. JADES is really a great data set to be able to apply this to. And I also mentioned here that the estimates for the mass completeness is around 7.5 log solar masses. So we're able to pretty confidently feel like we're probing some of those lower mass regimes on a complete scale. And then actually selecting the H-alpha line emitters. So this is done photometrically. So we look for H-alpha excess in this F356 filter there in the green and measure the excess photometrically from the optical continuum of the filters kind of flanking the F356, so F335 and F410M specifically. But then we select the H-alpha line emitters showing this excess in that non-overlapping region. And then also interesting to look at is not only these H-alpha, really actively star-forming galaxies, but also the population that's not this H-alpha selection. So to be able to probe some of these actively star-forming versus not populations of galaxies, we also look at all of the galaxies in good south in that same redshift range covered by the H-alpha emitters that are not selected by the excess H-alpha line emission. So just to put into context here where these galaxies lie on the main sequence, so you can see the H-alpha sample is in that dark purple color, and it's lying pretty consistently along the main sequence. I also highlight in the blue diamond some complex systems which in our analysis we found was interesting to kind of just keep in mind because a lot of the fitting analysis for the morphologies kind of struggled sometimes to be able to characterize what some of those clumpier systems like I show there, what the sizes are in the morphologies. And that kind of makes sense because even just visually looking at these, it's not super trivial to say, well, what does a size even mean for a galaxy like this? So even these types of systems kind of can bridge the gap a little bit maybe between some of these like star-forming cluster discussions as opposed to the more global galaxy scale. And then also in the gray, there's all of the non-H-alpha galaxies. So overall, a pretty large sample we were able to select. And actually measuring the morphologies of these, so we use a tool called ForceFo that forward models the PSF to match morphologies. So this is really important when looking at the multi-wavelength morphologies. And the strength of ForceFo in particular is that it works on the individual exposure level. So when you move to the mosaic, you actually lose a lot of that subpixel information that comes from the dithering of the exposures. So ForceFo being able to model the morphologies on the individual exposures really allows us to get to those compact sizes that some other studies using other morphology fitting tools can't necessarily do. And so I show here the combinations of filters that we simultaneously model together to probe the different star formation tracers. And I can talk in more detail about exactly, for example, how the H-alpha sizes are measured if anyone's interested in the questions. So thinking about results now, we kind of the first obvious thing to do was to put our sample on the size-mass relation on these different star formation timescales. So if we start with H-alpha, tracing the most instantaneous star formation, and I have an example there of kind of what a typical size looks like for these types of galaxies. So these sizes can go down to tens of parsecs. And if we look then, keep moving along the timescales, we start to see that evidence of really strong inside-out star formation. So we see, for example, here that the H-alpha sizes, as evidenced by the slope and the intercept that I show for the size-mass relations below, is about 2 times larger than the UV sizes. And taking a closer look into the UV sizes, by fitting 2 different regimes of that UV continuum, we're able to also disentangle a bit whether these changes in the size are due to dust effects because the UV is more sensitive than H-alpha to dust, extinction, or whether it's really due to the timescales. So what we see here is that there's really no strong dust gradient between the far UV and near UV sizes because they are pretty consistent. And so we can attribute these size differences to the difference in star formation timescale between H-alpha and UV. And then even looking into the rest optical continuum sizes, we see especially at the lower masses there below 10 to the 8 that there's a steep turnoff in what the size-mass relation is fit there. And so that's even stronger evidence for how strongly the inside-out star formation is happening along these different timescales. All right, and so taking a look at the non-H-alpha counterparts finally, what we see is that the non-H-alpha sizes are generally larger in the UV and optical than the H-alpha counterparts, but they seem consistent with the H-alpha sizes. So that really points to us probably seeing galaxies that experience some inside-out growth that we're actually tracing with the H-alpha sample separately. And taking a closer look into the variability of sizes in that scatter of the size-mass relation that we just saw, if we look between the H-alpha and non-H-alpha sample, we see in that upper right quadrant is where the inside-out star formation is happening because the far UV is larger than the optical sizes. But then we see with the non-H-alpha galaxies more of a variability in the physical mechanisms affecting the morphologies. So things like outside-in growth, or even where the burstiness is in the left-hand regime, those are probably mini quenching systems. So we really see more of that variability. And it's still something that I think is not completely well understood, so there's kind of a lot of food for thought there. But to summarize, just hitting the key points about where we're able to fill in some of the gaps that are existent in high redshift morphological studies with our large sample size and the completeness, the redshift range we're probing, and how compact the sizes are, as well as the specific the wavelength bands that we're able to probe, and then the evidence of the strong inside-out star formation that we see between the star formation tracers and the complexity of morphological evolution in the non-H alpha size scatter. So I'm happy to take any questions, and thank you.
Thank you very much. Very interesting. I have quite technical, but with some implication question. So you go very deep in terms of continuum, so you go very down in mass, but what is the detection limit in terms of H alpha emission? Because your filter is rather, well, not broad, but it's 1 micron width, for example. So how does this translate into H alpha emission detection limit, and how this could possibly affect your selection?
Yeah, so that's a good question. So I think I might have to think about that one a little more, but kind of initial ideas is maybe that I guess in detection like completeness limits, we're not so concerned with kind of like the smaller, being able to probe like those smaller sizes because we expect those to be the less. If they were like the more extended, larger sizes, then we'd have concerns, especially at lower masses with kind of lower surface brightnesses. So then at these smaller sizes, for example here, we're not so concerned that we may be like missing some populations of galaxies there. So specifically for H alpha, I'll think about that a little bit more, and we can talk maybe over coffee as well. But yeah, that's maybe my initial, impressions.
Yeah, is there any possibility that the difference in size is partly due to the fact that the ionizing stars are essentially ionizing a gaseous volume, a Strömgren volume that's much larger than the stellar cluster itself, just like nearby H2 regions, right?
Yeah, that's a good question. I think I'll have to think more about that one as well. Yeah, I think something that maybe we can also, look into with the SED modeling that we do for the galaxy properties is maybe some of these ionizing properties to better understand that as well.
Salvestrini, if you are in the room, please come to the registration desk. Thanks.